In this next module, I'm going to solve the same kind of probability problems that we solved in the last module, but instead of using probability trees, I'm going to use a little formula called Bayes' rule. It turns out that this formula is really important because it forms the foundation of a whole branch of statistics called Bayesian statistics, and we are going to touch upon Bayesian statistics a little bit in this course. It's not so important that you understand how to crank through using this formula. What's really important is that you understand conceptually what Bayes' rule is useful for, and we're going to go over that in this module. So I'm going to start out here with a brief little derivation of Bayes' rule. For those of you who are interested, if you really don't like derivations in algebra, you could fast forward through this part, but I think it's useful before you use a formula to have a little sense of where it comes from. So imagine that we've got two events, A and B. The probability of B can't be equal to 0 because we're going to put B in the denominator here. Another way to write the conditional probability of A given B is the following. You could say that that's equal to the joint probability of A and B divided by the probability of B. And let me kind of conceptually motivate this relationship for you. So imagine we have a probability space. So I'm going to use Venn diagrams now. Some of you have probably seen these before. But imagine we've got two events, A and B, and here's all our possible events. When we condition on B, what we're saying is we are now reducing the probability space down to B. We know B has occurred, so nothing that is not B can have occurred. So we're going to cross out the rest of this probability space. That's essentially what we're doing when we divide by the probability of B. We're reducing the probability space just down to B. Once you're in B, and you know you're in B for sure, what's the probability of A? Well, that's just the probability, the joint probability of A and B. So that's this probability here. That's the joint probability of A and B. Once I know that I'm in B, then the only probability of A is I have to be in this space. That's the probability of the joint probability of A and B. So that's the numerator here. So if you believe this relationship, if that makes sense to you, then the rest of Bayes' rule just falls out algebraically. And I'll just quickly go over the algebra. So if this is true, if the probability of A given B is just the joint probability of A and B divided by the probability of B, we can just do a little bit of algebraic rearrangement, multiply both sides by the marginal probability of B. And it's going to also be true, if you buy the first formula, you're also going to buy that it then must be the case that the probability of B given A is also the joint probability of A and B divided by the probability of A. So that must be true as well. We can cross multiply by the probability of A. What you'll notice is that these two equalities share a term. They both are equal to the joint probability of A and B, so we can just put them equal to each other. Then we can do a little bit of algebraic rearrangement, and we end up with Bayes' rule. This is Bayes' rule right here. So it's mostly just a little bit of algebra to get there. There's two ways you might see Bayes' rule written. So the first one is the probability of A given B is the probability of B given A times the marginal probability of A divided by the marginal probability of B. You may also see it with the law of total probability thrown in as the way to calculate the marginal probability of B. Usually often you don't have the marginal probability of B just available to you, and usually have to calculate it out. So that's a little bit more of a detailed formula, the second version. All right, so this formula looks complicated, it looks confusing. Why do we care? Why is it useful? So what is the Bayes' rule useful for? So notice that it does something extremely useful. It flips conditional probabilities. So if I give you the probability of B given A, then you can use Bayes' rule to get back the probability of A given B. So you can flip those conditional probabilities. That turns out to be useful for many reasons, such as when we do things like calculate positive predictive value. I think an example will help here. So let's go back to the example we had in the last module. We were dealing with an HIV test. And again, same assumptions. HIV has a prevalence of 3% in San Francisco, and this particular test has a false positive rate of 1 in 1,000, false negative rate of 1 in 100. I asked you before to calculate the total probability of testing positive. Now I want to know, what's the probability that a person who tests positive actually has HIV? This is also known as the positive predictive value. So let's calculate this using Bayes' rule. We calculated it, we've set it up already on a probability tree. So we can answer the question from the probability tree, and then we'll answer it using Bayes' rule. So using the probability tree that we set up in the earlier module, once you know that somebody has tested positive, then you know that you have to be on either branch 1 or branch 3. Given that somebody tested positive, they're on one of those two branches. So you've reduced your probability space to one of those two branches. Which of those branches also involves actually having the disease? Well, that's only branch 1. So the probability that you are positive, given that you test positive, can be calculated simply by dividing the probability of the top branch by the sum of the two branches. So it turns out you have a 96.8% chance of being positive if you test positive. So that's using the probability tree. The probability tree is always going to get you the right answer. But if you don't want to always have to write out these trees once you become good at them. So Bayes' rule is kind of a shortcut for getting there. So here's what it looks like in terms of Bayes' rule. So I gave you the probability of testing positive given that you are positive. That's the sensitivity of the test. But then I asked you to give me back the flipped condition, which is the positive probability of being positive given that you test positive. So to get that probability, we can apply Bayes' rule. I've written it in the first form here, and then I've written it with the law of total probability in the denominator. That's the way that we can calculate the marginal probability of testing positive just from a formula. So we can plug into all of this. So for example, the probability of testing positive, given that you are positive, that's your sensitivity, that's 99%. The marginal probability of having the disease is 3%, that's the prevalence of the disease. We put those same numbers in the denominator, as well as the marginal probability of not having the disease was 97%. The probability of testing positive if you don't have the disease was 1 in 1,000. Notice that again, that denominator is just that law of total probability. Notice we get the exact same answer. It's all the same elements that were on the tree. It's a faster way to do it than drawing out the tree. Again, once you get good at these, you don't need to draw out the tree every time, and Bayes' rule is a little bit of a shortcut. Let's do another practice problem. So suppose that we had, there was a company who contaminated 15% of a population with a dangerous chemical. So 15% of the country was exposed. And this chemical raises your risk of pancreatic cancer. And so say that you're the lawyer who's suing the corporation on behalf of a particular pancreatic cancer patient. You want to provide some evidence that your client's cancer was likely to be due, at least in part, to the chemical. However, your client doesn't know if she was exposed to the chemical. So let's say that if you were exposed to the chemical, your lifetime risk of pancreatic cancer is 0.0004. If you weren't exposed to the chemical, your lifetime risk is 0.0001. It's a relative risk of 4. You can use this information to calculate what's the probability that your client was exposed to this chemical. So we know what your probability of cancer is if you were exposed. But we want the conditional probability in the other direction. We want to know what's the probability that you were exposed given that you have cancer. So we can solve this using a probability tree, or we can solve it using Bayes' rule. So let's do the whole thing using Bayes' rule to start. So we have, again, we have the probability of pancreatic cancer given that you're exposed to chemical Z. I want to know the probability that you were exposed to chemical Z given that you have pancreatic cancer. That's what's useful for my client. Then we just apply Bayes' rule. So this is just an application of Bayes' rule. And then we can plug in to each of these. So first of all, what's the probability of getting pancreatic cancer if you're exposed? Well, I gave you that number directly. That's 0.0004. What's the probability of being exposed? Well, that was 15%. 15% of the population was exposed. That's the marginal probability of being exposed. What's the probability of getting pancreatic cancer? This one's a little bit more tricky. We have to use that law of total probability. So to calculate this one, there's two ways you could get pancreatic cancer. You are either exposed with 15% probability or you're not exposed with 85% probability. If you were exposed, your chance of pancreatic cancer is 0.0004. If you were not exposed, your chance of pancreatic cancer is 0.0001. So if we sum those up, that gives us the total probability, the marginal probability of getting pancreatic cancer at all in the population. When you add that up, it turns out to be 0.000145. So now we can just put those numbers in. So the probability of exposure in this case is equal to 0.0004 times 0.15 divided by 0.000145, and if you calculate that all the way out, that comes out to be a probability of 41.4%. We can also answer this using a tree, a probability tree. So if we were going to do it on the tree, the first branch point is whether or not you were exposed. So your chance of being exposed to Z was 15%. Your chance of not being exposed to Z is 85%. If you're exposed to Z, your chance of pancreatic cancer is 0.0004, which means your chance of not having pancreatic cancer is 0.996. If you were not exposed to Z, the pancreatic cancer risk was 0.001, so your chance of not getting it is 0.9999. We multiply across the branches, so your chance of having pancreatic cancer and having exposure is 0.00006. Your chance of having the exposure and not having pancreatic cancer is 0.14994. Your chance of not having exposure and getting pancreatic cancer was 0.000085. Again, just multiplying across the branches. The last branch is going to be 0.849915. If you add up all those probabilities, they're going to sum up to 1. So if you know that you've got pancreatic cancer, then you know you have to be on either this branch or you've got to be on this branch. Which of those branches involves being exposed to Z? Well, that's only the first one. So the probability of having the exposure, therefore, given that you have pancreatic cancer, is going to be equal to 0.00006 divided by the sum of those two branches, which is 0.000145, which comes out to be 41.4%. Same answer we got with Bayes' rule. Again, Bayes' rule is just a way to formalize this and make it simpler to calculate these directly. Now, the other thing to point out about the last example I gave you is Bayes' rule was a way of updating probability. So before you knew anything about the person, if you didn't know anything else about a person, a random person selected from this population, any random person selected has a 15% chance of being exposed to this chemical. That was the exposure rate for the chemical. So that person, before they got pancreatic cancer, had a 15% chance that they were exposed. Once we find out that they have pancreatic cancer, we've injected new information into the problem, and we're going to update our probability using Bayes' rule or a tree, and we find out that that person's probability now increases from 15% up to 41.4%. And this is what Bayes' rule is really useful for. It's useful for updating probabilities as new information comes in. And this next problem is going to illustrate that. So imagine we've got a box that has 3 coins in it. We know that there's 3 coins in the box. One is a 2-headed coin, one is a 2-tailed coin, and the other is a fair coin. You're going to reach into the box and pull out one of those coins, and somehow you're not going to look at which coin it is. This is a little bit of an artificial problem, but imagine you don't look at what the coin is and you just flip it. So all you get to see is what comes up when you flip the coin. So let's say you choose a coin at random, you flip it, and you see that it came out heads. So now what's the probability that the coin that you chose is the 2-headed coin based on the fact that it came up heads? And then what if you did it again? What if you take that same coin that you just flipped and it turned out heads? What if you flipped it again and it came out heads? What if you flipped that coin again and it kept coming out heads? Eventually, if it kept coming out heads again and again and again, right, eventually you're going to be pretty convinced it's a 2-headed coin. So this is the idea of updating probability. So let's go through this formally and answer these questions. So before we flip the coin, when we just reach in and pull one coin out of the box, we know there's 3 coins in there. One is the 2-headed coin. So our probability that we have the 2-headed coin is going to be 1 out of 3, 1/3. After we flip the coin and we get a head, how does that probability change? How do we update that probability? Well, we can use Bayes' rule here. So what is the probability that we have the double-headed coin given that we flipped a head? that is equal to the probability that we flipped a head, given that we have the double-headed coin, times the probability, the marginal probability that we have the double-headed coin, divided by the probability that we flipped a head. Overall, that's the marginal probability of flipping a head when you pick one coin out of the box. So that's just applying Bayes' rule. Then we can fill in each of these probabilities. So if you picked the two-headed coin, conditioned on the fact that you picked the two-headed coin, what's the probability that you're going to flip a head? Well, it's 100%. That one's easy, because if it's a two-headed coin, you have a 100% chance of getting a heads in the flip. What's the marginal probability of getting the double-headed coin? Well, that was 1/3. We had a 1/3 chance of picking out the double-headed coin. The hardest part of Bayes' rule is calculating the marginal probability here of flipping a heads at all. So how would we do this? Well, here's what happened. When we reached into the box, we either got the two-tailed coin with 1/3 probability. If that happened, we would have a 0% chance of getting a heads when we flip the coin. If we got the fair coin when we reached in the box, that's a 1/3 probability that that would happen, then we have a 50% chance of getting a heads. If when we reach in the box, again with 1/3 probability, we get the two-headed coin, we would have a 100% chance of getting a heads. So if you add all of that up, it's going to be your chance of getting the heads when you flip the coin turns out to be 1/2. So now we can just calculate out 100% times 1/3 divided by 1/2 is equal to 2/3. So once we flip the coin one time and it comes out heads, we now have a 2/3 chance that we have the two-headed coin. So we've updated our probability from a 1/3 chance to a 2/3 chance. All right, now starting there, now we have a new prior probability. This is what's called a prior probability. Our new prior probability before we do any other experiments is that the two-headed coin now has a probability, we have a probability of having the two-headed coin of 2/3. Let's say we flip that coin again and it comes up heads again. How do we update our probability? Well, we can again use Bayes' rule. So now again, what's our probability of having the double-headed coin given that we again flipped a heads? That's equal to the probability that we would flip a heads given that we have the double-headed coin times the probability of having the double-headed coin times the probability of flipping a heads at all. Well, again, if you got double-headed coin, you're guaranteed to get a head, so that one is just 100%. Now, the marginal probability of the double-headed coin, that's been updated, so now that's 2/3. We now, given the information from the last experiment, we now know that we have a 2/3 chance that we have the double-headed coin. Let's calculate now the hardest part, the marginal probability of flipping a heads at all when we flip that coin a second time. Well, there's two possibilities when we flip that coin a second time. There's a 2/3 chance that we have the double-headed coin. If that's the case, 100% chance we're going to get a heads. That's one way we can get a heads. But there's still a 1/3 chance that we could have the fair coin. So if we have the fair coin, there's a 50% chance only of getting a heads. There's 1/3 probability that we have that fair coin. So we can add all of this up, and we can see that we have a 5/6 chance of flipping a coin at all. That's our marginal probability of flipping a heads at all. So that's the marginal probability of flipping a heads in this experiment. So we can then do out the math here, and we end up that we have a 4/5 chance that we have the two-headed coin. So we've updated our probability. Now there's no longer a 2/3 chance that we have the two-headed coin. Now it's a 4/5 chance that we have the two-headed coin. And you could keep going with this and keep applying Bayes' rule. So again, this idea of Bayes' rule as updating prior probabilities. I now want to return to the Monty Hall problem, which I threw out as one of the teasers for this week. So again, the way that the Monty Hall problem works is you have 3 doors. They're on a game show. There are 3 doors. Monty Hall shows you 3 doors. Let's call them A, B, and C. Let's say that you say you want to see what's behind door A. But then Monty Hall comes in and he says, well, I'm going to show you there's nothing behind door B. And now he gives you the option to stay with your original guess, to stay with A, or to switch to C. And the question for the Monty Hall problem is, do you stay? Are you better off staying? Are you better off switching? Or does it make no difference? Now, for most people's intuition on this when they first see this problem is they think it's not going to make any difference. It's random, right, where the prize is. It's random which door you picked, so why should it make any difference if you stay or switch? That's most people's gut intuition. In fact, The answer to this problem is that you are much better off switching doors. There's a 2/3 probability at this point that the prize is behind door C. There's only a 1/3 probability that the prize is behind door A. And this is initially counterintuitive to most people. I've had to convince a lot of people that this is true. But so what's happening here, the reason the probabilities change, the probabilities get updated, originally there was a 1/3 chance of the prize being behind any given door, right? But the probabilities get updated here because Monty Hall injects information into the problem. He has information that he uses when he shows you the empty room, the empty door. That interjection of information changes our probabilities. And the best way that I can show you this is with a little simple little experimental setup here. Usually this will convince people. So here are my 3 doors, A, B, and C. And let's say that the prize, a quarter here, that the prize is behind door A. And I could have picked, it's random which door the prize is behind. So I could have picked any of the doors to put the prize behind, but let's just set up the scenario where it's behind A. It would be the equal for all the other doors. So if the prize is behind door A. All right, so imagine the prize is behind door A. Now, it's random which door you pick to begin with. So let's say just you randomly pick door A. You have a 1/3 probability of randomly picking door A. Let's say you pick door A. Okay, so the prize behind door A, you've picked door A. Monty Hall now comes along and he says, well, he knows that there's nothing behind B and there's nothing behind C. So it doesn't matter which door he shows you. But let's say he shows you B. Nothing behind B. Now, are you better off in this case staying or switching? Well, in this case, you're better off staying, right? Because if you switch to C, you won't get the prize. So that's one case. Let's do the next case, though. Imagine that the prize is still behind door A, but you happen to have randomly picked door B as your initial guess. Okay, so now what does Monty Hall have to show you now? So Monty Hall now has to show you door C. He cannot show you door A because the prize is there. And Monty Hall knows the prize is there. So this is where the information is getting injected into the problem. So he shows you, nothing behind door C. Okay, remember, you started with picking B. Are you better off staying with B or switching to A? You're better off switching to A. Okay, let's consider the last possibility where your initial random guess was to pick door C. If you pick door C, again, the prize is behind A, so Monty Hall has to show you what's behind B. There's nothing behind B. He says, should you stay or switch? Well, again, you're better off switching. So 2 out of 3 times you're better off switching. Only 1 in 3 times are you best off staying. Again, this is counterintuitive for most people, but it's a conditional probability problem because information is being added to the problem by Monty Hall. If you want to read more about this and do a quick little, the New York Times had put together a little interactive graphic that helps you understand the Monty Hall problem. So I'm giving you the link here if you want to do more on this problem.